Hello, and welcome to the TI Precision Labs video covering crosstalk on PCB layouts. This is part of a larger series on PCB layouts for good EMC. This series is specifically intended to cover mixed signal systems where the digital signals are less than 100 MHz and the clock rise time is greater than 1 nanosecond. This video looks at the factors influencing crosstalk between two PCB traces and provides measured results. The video also shows how ground poor can impact crosstalk. Finally, split versus solid ground planes are covered. Let's start by considering how PCB trace geometry influences the crosstalk between two traces. Crosstalk between two adjacent traces is a common problem. The parasitic capacitance between the traces will allow the signal from one trace to interfere with the other. The closer the two traces are, the greater the parasitic capacitance and the greater the coupling. Also, longer traces will have more parasitic capacitance and will have greater coupling. Signals with a fast rise time will introduce more crosstalk. A greater distance between the trace and its associated ground return path will cause the currents to spread out and mix together, causing crosstalk. As we have seen before, discontinuities in the ground path can cause RF emissions which will lead to crosstalk. Finally, ground poor between traces can reduce crosstalk if the poor is properly grounded with stitching via. On the other hand, if the ground poor is not sufficiently grounded, it can act as an antenna which will make crosstalk worse. When a signal is applied to a PCB trace, a magnetic field will surround the trace and an electric field will run from the trace to the ground return plane. The return current will travel beneath the trace for frequencies above 100 kHz. This slide shows how wide the return currents will spread out in the return path beneath the trace. The return current will spread out more when the height of the trace above the plane is increased. This is because increasing the height, or dielectric thickness, allows the field more room to spread out. Note that overlapping of the ground currents will cause crosstalk. The graph at the right shows the current distribution beneath the trace. You can see that the majority of the current is directly beneath the trace, but some small current density will exist far from the trace. The graph to the left is the integral of the current density plot. From this plot, you will see that 70% of the current will flow under plus or minus 2 times the height of the PCB trace. The PCB examples show the electric field for an 8 mil trace with a 4 mil dielectric and an 8 mil dielectric. These figures emphasize how changing the dielectric thickness or height causes the electric field and the associated return currents to spread out. Finally, the PCB example in the center shows how crosstalk can occur when the field from one trace overlaps the other trace. Based on the current distribution, you may adjust your trace spacing to minimize the overlap of return currents. In reality, the crosstalk is a function of both trace length as well as the spacing between the traces. So trace separation is more important for long parallel traces than it is for short traces. This slide shows measured crosstalk results for different trace spacing, length, and dielectric thickness. For the test, a 3.3 volt 10 MHz square wave with a 2 nanosecond rise time was applied to the aggressor trace, and the victim trace was driven with a logic low. The signal is routed on the top layer, and the ground plane is directly adjacent to the signal layer. The two dielectric thicknesses used are the minimum and maximum prepreg thicknesses available for most PCB processes. The graph on the left side shows how increasing trace length will increase crosstalk. Also, notice that decreasing the dielectric thickness significantly reduces crosstalk. The crosstalk is 0.45 volts peak to peak for the 3,700 mil long trace with the 14 mil dielectric thickness, but only 0.15 volts peak to peak for the 4.3 mil dielectric. The graph on the right shows how crosstalk is impacted by trace spacing. The tightest spacing used in this experiment was 8 mil spacing between the two 8 mil traces. This is the minimal trace spacing for many low-cost PCB processes. Tighter spacing can be achieved, but at higher cost. For 8 mil spacing on a 3,700 mil long trace, the crosstalk is about 0.45 for thick dielectric and 0.2 for thin dielectric. Doubling the spacing significantly decreases crosstalk. In fact, for a thin dielectric, increasing the spacing further has little to no impact on crosstalk. The crosstalk for a thicker dielectric continues to decrease all the way to a spacing of 32 mil. This slide was previously covered in the impedance matching section. We review it here because an impedance mismatch can greatly impact crosstalk. For termination impedances less than 20 ohms, there's a lot of overshoot, which translates to crosstalk. A slot or discontinuity in the return path is one of the most common reasons for crosstalk. In this picture you will see that the return currents will travel beneath the individual traces. These currents are separated enough from each other to minimize crosstalk. However, when the signals pass over the ground return slot, they will mix together, causing crosstalk and RF emissions. Let's look at some measured results. This slide shows two different experimental results. For the first experiment, a 10 MHz square wave is driven on a line adjacent to a line driven by ground. In this case, both lines are above a solid ground return path. The second experiment is the same as the first experiment, except that the signals travel over a discontinuity in the ground return path. The crosstalk for the experiment with the solid return path was 280 millivolts peak to peak, whereas the crosstalk with the discontinuity in the ground return path was 527 millivolts peak to peak. Thus, the poor grounding almost doubled the crosstalk. Let's look at how the RF emissions were impacted. This slide shows the ambient noise floor, the RF emissions over the ground discontinuity, and the RF emissions over the continuous ground. The RF emissions for the circuit with the ground discontinuity were 56 times larger than the continuous ground plane. This measurement helps illustrate why discontinuities in the ground return path are a leading cause of EMI issues. This slide covers another common PC board layout error. Some engineers will create a separate analog and digital ground plane in order to avoid corrupting the sensitive analog with crosstalk noise from the digital communications. Frequently, the two ground planes are connected together at one point near the ADC with a 0 ohm resistor, inductor, or a ferrite. This approach was widely promoted 30 years ago. It turns out that in general this is not a good approach. Signals that traverse the split will have large emissions and frequently have poor analog performance. Using an inductor or ferrite can generate large transient voltages when switching currents pass from the digital to the analog section, and this could cause data errors and even damage the device. For engineers who really want to use a split, a better approach is to use a ground bridge, as shown in the center drawing. The ground bridge needs to be wide enough to allow any traces to pass over the bridge and not over a split in the ground. The best grounding choice is to simply use a solid plane and to make sure to keep the physical distance of the digital and other noisy signals away from the analog. The process of physically segmenting the different signal types to different sections of the PC board is called floor planning. And a good floor plan is a much better approach to minimizing coupling of digital into analog than a split plane. A common practice used to minimize coupling between traces is to use a ground pour between the traces. The idea is that the signal will couple into the adjacent ground pour rather than into each other. Ground pour can be effective if it is well tied into other ground planes with vias, but it will make things worse if it is not. In the picture shown, the ground pour is connected to the ground plane with many vias. Ideally, the spacing between vias would be at most 1/10 wavelength, and all edges of the pour should have a via. Any long ground fingers need vias on their ends. To find the maximum frequency for square waves applied, use the RF bandwidth equation where the frequency is calculated as 1 over pi times the rise time. Using insufficient vias or having floating copper can make the pour act like an antenna, which can actually increase the crosstalk and cause RF emissions. To prove the importance of stitching vias on ground pour, I did multiple experiments. For each experiment, the circuit and layout were the same, except different copper fills were used. First, the fill was eliminated and the space between the trace was 34 mils and the length of the trace was 3,700 mils. For the no fill configuration, 40 millivolts peak to peak of crosstalk was measured. Adding floating copper between the traces made the crosstalk increase to 60 millivolts peak to peak. Grounding the copper pour on one end made the crosstalk increase to 86 millivolts peak to peak and created a resonant ringing effect. Grounding both ends of the pour with stitching vias showed good performance and the crosstalk was negligible. The rule of thumb for copper pour is that it should have stitching vias in 10th wavelength intervals, so grounding both ends may not always work well. If you plan on using copper pours, I would be careful to use sufficient vias so you don't end up creating an inadvertent antenna. This slide summarizes the measured results for copper fill experiments discussed on the previous slide. The layouts at the bottom show the example with no pour and a ground pour with many vias. The same circuitry and PC board layout geometries are used in each experiment except that the pour is changed. The oscilloscope waveforms show the 3.3 volt 10 MHz square wave applied to the aggressor trace in yellow, and the crosstalk is shown in the red trace. The range on the red trace is 20 millivolts per division for all measurements. Moving from left to right, you can see that the circuit without the pour has about 41 millivolts peak to peak of noise, whereas the circuit with floating pour has significantly worse crosstalk at 60 millivolts peak to peak. When the fill is only grounded on one end, it acts as an antenna and has a crosstalk of 85 millivolts peak to peak with resonant oscillations. When the ground pour is used with two vias on the ends of the fill between the traces, you get nearly zero crosstalk. Adding many vias to the ground fill doesn't have a significant impact on crosstalk and looks very similar to the case with minimal vias. Please do not conclude based on this experiment that you should use minimal vias. The recommendation is to space the vias in 10th wavelength increments for the maximum frequency content expected on the board. Remember, the maximum frequency is set by the rise time of your signal and is calculated as 1 over pi times the rise time. This slide shows a similar layout to what was previously shown for using copper pour. However, this example has a few issues that would cause crosstalk and RF emissions. Can you find them? One issue is that some of the copper fill does not have a via at the end of the trace. These copper fingers will act as an antenna for RF emissions and will increase the crosstalk. Another issue is that there's a floating island of copper. A key point here is that it would be much better to avoid using the copper pour than to have an improperly grounded copper pour as shown here. That concludes this video. Thanks for watching. Please try the quiz to check your understanding of this video's content. Question 1. Which factor does not impact the crosstalk between two PCB traces? The correct answer is B, the copper thickness. Signal rise time, trace length, trace separation, and PCB dielectric thickness all have significant impact on crosstalk. Question 2, true or false? Ground pour can actually make crosstalk worse if it is not done correctly. The correct answer is A, true. If the pour is not well connected to ground with many via, it can actually make crosstalk worse and cause potential resonances. The via should be at all ends of the pour and should ideally be spaced at a maximum of 1/10 wavelength increments. Question 3. Using the graph below, what peak-to-peak crosstalk would be seen on a 3000 mil trace with a 9 mil dielectric thickness? For this example, the trace spacing is 8 mil and the trace width is 8 mil. The correct answer is B, 0.25 volts peak to peak. In this case, you will have to interpolate between the two curves. A 3000 mil trace length with a 4.3 mil dielectric had a crosstalk of about 0.17 volts peak to peak, and the 14.3 mil dielectric had a crosstalk of about 0.36 volts peak to peak. Interpolating between the two curves gives approximately 0.25 volts peak to peak for a 9 mil dielectric. Of course, this is just an estimate, but it does give a general idea of what kind of crosstalk to expect. Question 4. What is a potential issue with the PCB layout below? The correct answer is C, all of the above. One general issue with all two-layer boards is that the top and bottom layers are separated by a large distance. This will increase crosstalk. Of course, in some cases, cost requirements necessitate the use of two-layer boards and you will have to tolerate the degraded performance. Another issue is that the copper pour is not optimally grounded. One trace in particular has a finger that is not grounded on one end and will act as an antenna. That's all for today's video. Thanks for watching.